Hello, hello. All right, we're going to get started so that we can stay on time today. So I'll ask folks to wrap up conversations and grab seats. If anybody's listening. I don't know if anybody's listening to me. Sounds like no. Okay. All right, we are doing our best to stay on time today. So I am thrilled to introduce Marios from IBM, who's going to be talking more about the GPU work we are doing. Velox.
Thanks a lot. I'm Marios. I'm a software engineer at IBM based in Zurich. And the title of my presentation is Moving Bytes at the Speed of Light. So my presentation consists of two parts. First, I'm going to talk about GPU to GPU Exchange. That is a feature that enables GPU to GPU data transfers across Presto C++ workers. And the merging process of GPU to GPU Exchange in upstream Velox is still in progress. And the second part of my presentation is going to be about Zephyr. Zephyr is a distributed high-performance I/O system that lets us fetch data faster from object storage, and it provides a distributed caching layer that is based on Velox async data cache. But before diving into the details of GPU to GPU Exchange and Zephyr, I wanted to give you a brief summary of the hardware that is available today versus the hardware that is going to be available soon, so that we know what we're talking about. So on this slide on the left, you can see the GB200 NVL72 rack from NVIDIA that consists of 72 Blackwell GPUs achieving up to 5,760 teraflops, having a GPU memory bandwidth of 576 terabytes per second, and the GPUs are connected with an NVLink network having a bandwidth up to 130 terabytes per second. And on the right side, you can see the Vera Rubin NVL72 rack that is announced from NVIDIA, and this consists of 72 Vera Rubin GPUs, achieving up to 9,360 teraflops, twice as the Blackwell architecture, having 3 times the GPU memory bandwidth compared to GB200, up to 1,580 terabytes per second, and having an NVLink network that is 2 times faster than the one in the GB200, achieving up to 260 terabyte per second bandwidth bidirectional. So I wanted with this slide to make it clear that GPUs are starving for data processing. And if we think about the cost-performance ratio, the busier the GPU is, the better the cost performance we get. So how can we keep the GPUs busy? By delivering the data faster. And that's what we're going to do with GPU to GPU Exchange and Zephyr. So I'm going to start first with a GPU to GPU Exchange, a new feature that we introduced to Velox. Thinking of Prestissimo multi-GPU overview, we have multiple Presto C++ workers, each one pinned to a single GPU. And we have the Presto coordinator that assigns plan fragments to those Presto C++ workers. Each plan fragment consists of multiple pipelines, and each pipeline is a sequential series of operators. Now, if we want to get this massive performance advantage from the GPUs, we must never leave the GPU during a query execution. And inside the single pipeline, this can happen because almost all the operators are supported from CuDF, so we never leave the GPU. But what happens when 2 or more Presto C++ workers want to exchange data between each other? In that case, Presto by default is using the so-called HTTP exchange, and as the name of this mechanism implies, the HTTP protocol is used, which is very, very slow. So what happens when we have a GPU cluster and we use the HTTP exchange? We have 2 major performance implications. First of all, we need to leave the GPU and go to the CPU. So we are bottleneck from PCIe throughput that is 32 gigabytes per second for PCIe 4 and 64 gigabytes per second for PCIe 5. But the second one, which is even more important, is that we use HTTP, so we will never reach even that throughput. And when we have systems like the ones that I presented in my first slide, we have NVLink bandwidth connecting the GPUs, and we want to be limited from the maximum throughput of the NVLink that is up to 300 gigabytes per second for NVLink 3, up to 900 gigabytes per second for NVLink 5, and this is going to be doubled in Vera Rubin architecture, up to 1.8 terabytes per second. So we want a mechanism that understands the hardware and makes use of NVLink if it's supported instead of the HTTP exchange. And this mechanism is called UCX exchange or GPU to GPU exchange. As the name implies, this exchange is using UCX network library. UCX automatically discovers all the available data paths and selects the fastest route based on the system topology, for example, NVLink in that system. So UCX exchange enables efficient GPU to GPU communication without manual tuning. So if we focus on a single VM, that in that case consists of 8 GPUs connected with NVLink, you can see the NVLink switches with a green color. If we use our UCX exchange and we want to transfer data between 2 GPUs that belong to the same VM, UCX exchange is going to pick NVLink in order to transfer data between GPUs on the same node. Now, if we have 2 of those VMs and we want to transfer some data between 2 GPUs that belong to different VMs, then UCX is going to use those orange RDMA-capable network interface cards, and it will perform a GPU direct RDMA for inter-node GPU communication. GPU direct RDMA means that we're never going to go to the host. So the path is like we start from the source GPU, we go to the RDMA-capable NIC on the first VM, then to the other side on the RDMA-capable NIC of the second VM, and then directly to the GPU of the destination VM. So how exactly UCX exchange is designed to fit Velox? On the left side, you can see a CuDF partitioned output operator that creates multiple partitions, and each partition has multiple CuDF packed columns. And on the right side, we have a Velox sync operator. And, if you think about it, the Presto coordinator is telling the right side, the Velox sync operator, that you need to receive data for a specific partition from multiple remote workers. And for that to work, we introduced a UCX exchange operator that upon receiving this message from the Presto coordinator, it creates a UCX exchange source object for each worker that it needs to receive data from. And this UCX exchange source on the right side is going to establish the connection over UCX with the left side where a UCX exchange server object is living. And then we have the data flow from the left side to the right side. The UCX exchange server is going to train the queue where the CuDF packed columns for a specific partition are stored. It will transfer them to the other side over UCX, exactly as I mentioned before, where a UCX exchange source will place them in a UCX exchange queue, and then the UCX exchange operator on top is going to train that queue. It will unpack the data for that partition, and it's going to pass the data upstream to the Velox sync operator. And this is going to happen for all the remote workers that are sending data for that specific partition in parallel. Now, talking about the performance using UCX exchange, in that case, we run TPCH SF1000 using 8 NVIDIA 800 GPUs, and this system supports NVLink. And we wanted to compare the performance using UCX versus when we're using the default HTTP exchange that Presto provides. And we see that we're always faster with UCX exchange, but especially for queries that are exchange heavy like query 9 and query 21, we see a massive performance advantage improvement. Especially for query 9, we see that it's 22 times faster compared to HTTP exchange. Now, another experiment, here I used a G7E.12x large VM from AWS that has 2 NVIDIA RTX Pro 6000 Blackwell GPUs. And I ran again TPCH SF1000 with HTTP exchange and with UCX exchange. And we see that we go from 1026 seconds down to 112 seconds when we're using the UCX exchange. And this is one order of magnitude faster, as you can see. Now, if we run the same experiment, but we make the GPUs not be collocated as in the first scenario, so we have 2 of those VMs, but we use 1 GPU on each VM, then we need to go over the network. And we see that for HTTP exchange, query 21 goes out of memory. Why? Because the latency increases of the HTTP protocol, because now we need to leave the VM and we need to go over the network. And this results to data staying more in GPU memory, and that's why query 21 goes out of memory. Now, if we use the UCX Exchange, we get the exact same performance as in the first scenario where the GPUs are co-located in the same VM. And this happens because, as I mentioned earlier, UCX is going to pick the GPU direct RDMA for a GPU to GPU transfer over those RDMA capable NICs. So that was everything about UCX Exchange, and now I'm going to move to the second part of my presentation, that is about Zephyr. So as I mentioned earlier, Zephyr is a distributed high-performance I/O system that lets us fetch data faster from object storage, and it provides a distributed caching mechanism layer that is based on Velox async data cache. Before analyzing the architecture of Zephyr, I wanted to show you this slide that I borrowed from Greg's NVIDIA GTC presentation. That is a breakdown of Presto GPU operators for TPCH SF100 on the left side, and TPCH SF1000 on the right side. And we can see from these pie charts that the table scan operator takes up to 74% of the total execution time for SF100 and up to 61% of the total execution time for SF1000, which means that fetching data and decoding data is a very expensive process, and we need to optimize it further. Now, I'm not going to talk about decoding Parquet data in this presentation. I will focus mostly on fetching data from object storage. So, as you know, a lot of clients have their data stored on object storage that can be Amazon S3 or Azure. And in that case, we need to provide a mechanism that fetches the data fast. So what happens on a Presto C++ worker nowadays without using Zephyr? The worker is going to fetch the data from S3, in that case, using the default AWS SDK S3 reader. It's going to cache the data in the Velox async data cache, and then it will decode the data on the GPU of that worker. So we moved from this version to the Zephyr architecture, where we disabled the Velox async data cache on the Presto C++ worker, and instead we moved it to a separate Zephyr server process, whose purpose is to fetch data from S3, cache them in the Velox async data cache, and then stream the data as fast as possible to the Presto C++ worker's GPU memory. So I wanted to focus on three things. First of all, the Zephyr server can live in a VM where no GPUs are existing. We don't need GPUs on the Zephyr server side. We just need memory. Secondly, we optimized the S3 reader so that we can fetch data faster from S3 even when we're using a single Zephyr server. And third, for copying data from CPU to GPU, we use exactly the UCX exchange mechanism that I described in the first part of my presentation. So we let UCX pick the right path for a CPU to GPU transfer in that case. Of course, the goal is not to have only a single Zephyr server, but to have multiple Zephyr servers and let them fetch data and cache data in parallel. So the architecture looks like that. We have multiple copies of the Zephyr servers. The Presto C++ worker is distributing the requests over gRPC to the fleet of the Zephyr servers, and then we let them read data in parallel, cache data in parallel, and stream back the data to the Presto C++ worker's GPU memory using CPU to GPU RDMA over UCX, using UCX Exchange. So the advantages of the Zephyr architecture is that, first of all, we minimize the cold query execution time. Why? Because, first of all, we improved the S3 reader so that we can fetch faster from S3. And also because we increase the bandwidth by reading data in parallel. Secondly, when we have our data already cached in Velox async data cache, we can just stream them back without any extra copy, where just streaming the data from the CPU, from the memory where they're located on the Zephyr server, directly to the Presto C++ client's GPU memory. Third, we can scale out the Zephyr servers on demand. So based on the amount of memory we're using at the scale factor that we're running, we can create as many VMs as we want and run as many Zephyr servers as we want. So the RAM that we have in total is aggregated across those multiple Zephyr servers. And finally, we have a persistent cache across Presto cluster restarts, which means that if we run an experiment in a Presto cluster and we fetch all of our data across a fleet of Zephyr servers and then we restart the Presto cluster, this is not going to invalidate the cache. So second time we run the experiment, all the data are going to be there in the Zephyr servers. Now, talking about Zephyr performance results, the first experiment was to use a single G7e.12x large VM from AWS that has a single GPU, and they run a TPC HSF100 with and without Zephyr. And if Zephyr is enabled, we're using a single C7GN.16x large, a VM that does not have GPUs, as I mentioned earlier. And we see that for the cold execution time, we go from 45 seconds down to 29 seconds. And that's why I mentioned earlier that even with one Zephyr server, we can be faster than the current Presto C++ worker because we improved the S3 reader. And that's how we can minimize the cold execution time. And for the warm, we see that it's exactly the same because if the data fits in memory, then we can just stream the data to the Presto C++ worker, and that's a proof that the gRPC is not introducing any other overhead. Now, of course, we want to scale with the Zephyr servers. We want multiple of them. So if we go to a higher scale factor like TPC HSF1K, in that case, I use the same VM but 2 GPUs, and I run TPC HSF1K with and without Zephyr. And if Zephyr is enabled, we use now 2 CHGN.48x large VMs. And we see that for the cold case, we go from 245 seconds down to 138 seconds. And that is like almost twice faster. And the warm case is exactly the same because of the reasons that I mentioned earlier. And now another example. What happens if we just want to fetch an 8 GB file using 3 Zephyr servers, each of them using a CHGN.24x large VM. So as you can see, each of those VMs is equipped with a 300 Gbps NIC, and the Presto C++ worker is living in a VM where there is a single 400 Gbps NIC, and we fetch this 8 GB file that can be a Parquet file, right? And in this case, it's a Parquet file. We fetch it multiple times. As you can see, first time we fetch the file, this is cold. So when we start the Zephyr servers, Velox async data cache is empty. So first time we achieve 20 gigabytes per second throughput on the Presto C++ worker. And from the second time and on, all the data is already cached in Velox async data cache across the Zephyr servers. And having a 400 Gbps NIC on the client means that we can reach up to theoretical 50 gigabytes per second. 45 is the actual maximum throughput that we can get, which means that the Zephyr servers, when they have the data cached, they can fill up the NIC on the client side. And in that case, since we have 3 Zephyr servers, we see that each of them can push up to 35 gigabytes per second since we have a 300 Gbps NIC in each of those VMs. So if the client has 2 GPUs, each one connected to a NIC, then we can just have the exact same results per client. So those 3 Zephyr servers can fill up the 2 NICs on the client side, 2 400 Gbps NICs. So as a wrap-up, GPUs keep getting faster and faster, but I/O still remains a bottleneck for data processing applications. And using UCX Exchange, we can unlock the GPU to GPU performance, making use of UCX library that automatically selects the fastest path. That can be NVLink or GPU direct RDMA across VMs regarding the GPU to GPU transfers. and we can use Zephyr in order to fetch data from object storage and cache them using this distributed caching mechanism that is based on Velox async data cache, resulting to end-to-end moving bytes at the speed of light. That was the title of my presentation. So thanks a lot for attending. If you have any questions, feel free to reach me out in the coffee break. Thanks a lot.